it may not be the end all be all. I'm not silly enough to believe that, but it really opened up the mind and potentially opened up the emergence of high volume, low cost production of small things, small satellites, to could you do even bigger things on orbit instead of just being stuck with a CubeSat and that's all you can do? What if you could merge a bunch of them together, right? So that really potentially, I mean, it's almost unlimited what you could potentially do.
Well, we're back with another episode of the Cold Star Project. I am here with David Barnhart. He is the director of the University of Southern California's Space Engineering Research Center. We're going to get into that. He's the CEO and co-founder of a company called Arkisys. I hope I pronounced that right. And he has been a program manager at DARPA. So really interested in having you on, David. Thanks for being here.
Absolutely. Thanks for the opportunity. Appreciate it.
All right, Dave. Well, let's get started off with a little bit about the Space Engineering Research Center. What do you folks do there?
So I like to refer to it as a space engineering teaching hospital. I've always been sort of jealous of the medical school colleagues because they can essentially do anything and get money from anywhere. And the hard engineering sciences, we tend to don't do that. So my thought was the way that I work here is I really into hands-on, and everything that I do that relates to students, I don't do theory. I very rarely do experiments. Instead, we actually create prototypes. Everything's hands-on. So this engineering teaching hospital concept is where the faculty and the staff are the doctors, and the students come in as the residents, and we have to keep the satellite alive, basically. So it's not a live human, but it's it's real projects with real deliverables and schedules and costs. So it's very similar to essentially how industry operates and works. So that's what we do.
In industry, we've experienced a 40+% failure rate for small sats. So there is a lot of work to be done here. About how many students are going through at any point in time?
Yeah, so in the semesters, I typically have anywhere from 10 to 15 that are here on a regular basis. In the summers, I have 20 typically that are interning or doing either various volunteers. I'm lucky enough that I actually have this past semester 2 Italian students that are getting their graduate's degree. I host a number of French Air Force lieutenants from the Air Force Academy in France. They actually have to do outreach for their last senior year for projects to do research, which is actually a very cool concept and idea. I have community college students that come in, and last year was my first year that I hosted high school students to come in. So,
wow. Okay. Yeah. So quite an age range in there as well.
It is. And that's, so last semester I did a pilot project to start for a 1.5U CubeSat project that was based upon a course, but the course went from freshmen to second-year graduate students. And again, this concept of putting hands-on hardware is really also about collaboration. And so mentoring can occur at almost any level. And so that was a class that we attempted to start the project of hardware hands-on activities in support of a range of skill levels where there's a lot of collaborative interaction between the students.
Well, tell us more about that, Dave, because you obviously came up with that idea. Okay, let's have some mentoring at different levels and that, and invite a whole range of people in here. What happened in there once you get humans involved with something? Things tend to turn out a little different than what you expected. What was the most surprising outcome of that experience for you?
Yeah, so let's see, there was a couple of them. The one which I think we sort of all realize, but to see it in play is always interesting, is that younger individuals with less experience sometimes can pick things up much faster than individuals who state that that's their subject and that's their expertise, in all honesty. So that's been interesting. I've had some outstanding undergraduate students, and even to the point where I've had community college students that have outperformed even some of the graduate students. It's so that's sort of fascinating and very encouraging to see. And the interesting thing is it says that there is almost untapped potential if you can reach in to, whether it's the community college or the lower level students, to give them these opportunities, and then they can find their affinity to actually go off and execute, whether it's hardware or not.
Okay.
The other one is that just because people say they like to work with each other, it doesn't always work that way. So but I have a very dynamic group of individuals that always happens. The other thing that's really interesting is that USC is one of those places that has a large foreign student population, and it makes sense when you think about it. The foreign national students tend to be sort of hungrier or want to experience more of this, and it makes sense because they're only here for a short period of time, so they want to try to get as much as they can out of it, right? So that's sort of interesting to see as well.
Well, I like what I hear. It's good for the university because fees are generally higher. They're more intense about what their experience desires are and the outcomes that they want. I also like what you said about the more new type folks coming in and seeing stuff that a more experienced person might not be able to see. In the sales field, we call that the curse of knowledge, where you know something and so you just kind of blank it out and go, well, everybody knows that, and then refuse to kind of see the obvious. So one of the big reasons I wanted to have you on, Dave, is that you talked about a couple of things in your LinkedIn profile that I really like. Satellite design synthesis to cut down design time. I'm going to ask you about that in a second. And then hybrid robotic concepts for robotic assembly and repair craft. These are ideas that I've also had. You've taken them much farther than I have, I'm sure, from the fantasy level that I've had. But I love modular construction and things that can fix themselves. So let's begin with this. You say you have developed satellite design synthesis tools to cut design time down to days from months. Tell us a little bit about what that was like.
Yeah, so that was a project that we started several years ago. I've been on a number of satellite projects, and even today, I'm sure if you talk to the folks, one of the biggest challenges is in the integration phase, and in particular in the connectivity of the computational processes and interlinking between various components. So typically today, unfortunately, everything is still very custom. Custom design, custom connectivity, and custom software. So we attempted to attack that problem in two different ways. The first way was, can you do integration of components when they are not physically in the co-located space where the satellite's supposed to go together? And the thinking behind that was, integration only happens when the physical hardware arrives. But in space, unfortunately, because there isn't large productions and there's not an Amazon.space store that you can go get reaction wheels off of, it takes months and months and months in order to get that hardware. But you really like to test prototypes or engineering models as soon as possible, right? In many cases, vendors don't necessarily supply that. So the thought was, what if we supplied some sort of cyber physical interface, an Arduino board or something, to the vendor? They have engineering models at their location, have it set on the table, connect it to it, and then connect it to the internet. We can then essentially act like we're operating with the device in our laboratory, but do it over the internet. So we actually demonstrated that and proved that it's possible. That the technical challenges that people threw at, your latency is going to kill your ability for the system to operate. There's no question there was latency. We dealt with that basically by just changing the clock cycle in the processor. Instead of 100 hertz, you make it much less than that, and then the latency falls within that, right? So that was one idea, and then we took that to the next step, which was, well, okay, how might you integrate things even faster than that? And one of the key challenges is that when you have a component, you have to write code for it. Now, sometimes vendors provide a driver, if you will. Happens all the time in the computer, right? You have a new printer, you download the printer driver, and it goes into the central processor. It doesn't always happen with spacecraft that way. And there's a number of initiatives that have tried since the time we came out with this to attempt to do that from an open source standpoint. So the thought was, well, what if we could actually have a library of those control codes, essentially, that we could then hook in anything. Either the internet would do it, we would connect to a piece of hardware in the internet via the internet, or we write our own simulation code to be able to support that. So the other thing that we really wanted to do was, how do you build the software stack based upon the hardware that you get? Because that's the other thing, it's fascinating that happens, whether it's through supply chain challenges or whether it's a late design, you switch from a ball reaction wheel to a Blue Canyon reaction wheel. Those are different software requirements. So that takes time. So what we ended up doing is we created an XML schema that had a list of, 800 different components that we were able to put together. And in that schema, we would tie it to a mission design, a very simple mission design simulation that we had, such that you could actually, you put in a mission design, whether it's remote imaging at a particular altitude, and it would run through and select the components that would make up what's needed to satisfy the requirements of a particular mission. And then once that was done, in the schema, we actually had, it wasn't all populated, but some of them had a set of software code that was already written for that piece of hardware. And then the concept was that you put in the mission, the system runs it, develops a spacecraft, goes and pulls the code from a repository and builds a software stack such that you could actually go begin to test it. So that was the big construct behind it. Could you go from mission all the way to a software stack that you could then plug into either hardware you had or go through the internet to test with vendor hardware?
Great ideas. I like that a lot.
Yeah. And that was the way to try to cut down time, right? It's everything is always time, and time translates obviously to money and schedule, but integration and putting the things together, that tends to be the most difficult time.
All right. Well, let's see. I was talking to our technical engineering advisor, Dr. Rick Fleeter, and he was reminding me the manufacturing costs of small sats reportedly are about a quarter of the total cost of the launch. So how do you express the impact of these time savings? This should be a pretty easy question to answer, but.
Yeah. So, and definitely say hello to Rick. I've known Rick for many years. That's awesome. Yeah, so the issue of time relative to specifically spacecraft is it really adds up to cost, but it's an aggregated cost, and the aggregated cost comes to not just the satellite provider or vendor, or the payload provider or vendor, which may or may not be a customer, a user, but it also translates honestly to the launch vehicle provider. And what's fascinating, if you lay the timeline out for a space program, and you lay in launch, and you lay in what the spacecraft is supposed to do and where the payload comes in and the integration, and then on top of that, you have the development for the ground station to make sure that you can, whenever you send this thing up here, you can actually communicate back down again. All of those things, unfortunately, never lay on top of each other in a nice, even fashion. So any way that you can get the satellite integration time shorter and shorter and shorter, what essentially it translates to is that if the launch vehicle time is a fixed amount and you're trying to hit the launch vehicle time, forget about the fact that the launch vehicle guys constantly slip. Let's assume that stays the same. You'd like to have more time in between to validate the payload, which is the revenue generating portion or the mission generating portion, and they call them compatibility tests with ground station suppliers. So you'd love to be able to do as many of those iterations before you even get to the launch vehicle side. Any delay in pushing out the satellite, the other thing that it does, in all honesty, besides saving money, it decreases risk. Because the one thing, unfortunately, that bites every spacecraft provider is that as the satellite time continues to grow, there was an integration and test time that you had set that you knew you were going to solve everything. It constantly shrinks and shrinks and shrinks until you've basically, and you can actually, I know you could do this. You could create a graph that shows as the integration and test time shrinks, the risk for the project goes up.
Right.
So that's the really big thing, that if you can get that integration and test and the interaction between all of the various attributes on a spacecraft as well as the payload and flush it out as quickly as possible, you decrease the risk that anything is going to go wrong once it gets in orbit. So, and unfortunately, risk also translates to cost, or it's actually in the back end once it goes to orbit. If it's not working, you're not generating the revenue, you're not generating the mission data that you need, which eventually translates to lower revenue coming in.
Right. And, a lot of our listeners and viewers are engineers, and they have a lot of self-confidence, and they kind of have to. But the fact of the matter is, small sats have a terrible full and partial mission failure rate. It's terrible. It's 40+%. Yeah. So despite the fact that everybody thinks that they're really smart in the industry, we'll fix that, this integration issue is critical. Maybe the material and labor components of the costs are a quarter of the cost compared to 3/4, of the total being launch costs. But if you get this wrong, it doesn't matter whether you had a successful launch or not, because the thing doesn't work, and it doesn't give you what you want. Yeah. So this is key. Right. Yeah. You can't afford to be second best. You need to be first, and that requires speed. Now, if you're thinking that growth is supposed to be slow and steady, frankly, the way I was taught back in the 90s in the operations management and business administration programs, you are too slow. We have to adapt. And in space, it's no different than anywhere else. People like to think they're special in space, and it is fun, all the stuff we get to work on, but business is business. The fundamentals nowadays are conservative growth is not good. You need to run as fast as you can and risk outstripping your supply lines, which means in our world, using up the capital that we've got. That's a risk. But there is no prize for second place. There certainly is no prize for third. If you want to scale operationally fast, come talk to us at Cold Star Tech. We are the process experts for scaling fast. Now back to the interview. So I want to hop back to some DARPA projects that you have, where you developed hybrid robotics concepts for satellites. And we're talking about robotic assembly and repair craft. I am very interested, obviously, if there's security or compliance issues, don't talk about those. But in general, if you could tell us about the capabilities and experiences you had on these projects, that would be really neat.
Yeah, no, I appreciate that. DARPA is actually a very cool place where it actually encourages you to, to think, again, to think out of the box. And those words are way overused.
Yeah.
And it means different things to different people. But I was lucky enough, honestly, and honored to be able to go there and to actually do that. So the idea that eventually translated into what was called the Phoenix Project was really born on the seeds came from this concept of how do you shorten the design time to get something in orbit, right? That was the seed. The second sort of major input was if you have the ability to reconfigure once you launch something, what would that mean? Those two sort of entities eventually merge themselves together. When I started to ask the question of, why do we build spacecraft as monolithic entities? And how would you allow that reconfiguration to work? So in the end, the answer was that the only way you can enable a reconfiguration or an aggregation or an assembly or a disassembly is to completely rethink how we think of spacecraft today. And so that was the genesis behind the cellular morphology, which sort of was, again, inspired by biology. It's sort of fascinating. I've written some papers and I put them out there, and it's really interesting when you look at the cell types inside the human body, or inside a simple cell, a single cell or even dual cell. There's only a handful of types of cells, whether it's nerve transmission cells, a motive cell, a structural cell, right? There's only a handful. And what's really interesting is if you look at a spacecraft and how a spacecraft is put together, it's exactly the same way. There's structure, there's propulsion, there's power, there's attitude control. So you could essentially say, if you thought about it differently enough, or you re-architected it, you could argue that each one of those might be their own cell of some sort. And so that was the genesis behind it. So we created the construct of cellular morphology, and then the term satellite was born. Companies bid on it. There's a company that is now down in Southern California that is actually developing satellites. They have a particular brand name for them. They call them HiSat, but nonetheless, it's a satellite. At the same time that was going on, Germany was developing their own concepts of cellular morphology, or things that can connect. And what's interesting is aggregation can occur on a spectrum between homogeneity and heterogeneity, whether it's a single cell or it's a system cell. You know, when we first started, it didn't really matter. Just see if you can come up with it. So the other thing that's interesting that happened is that to put things together in space, the typical methodology we use is robotics. That's what we think of, a manipulation. What's interesting is on the ground, when you assemble something, you typically have your manipulators and you can put them together. In space, you really have to think through that, and it drives a number of technical attributes on the cell as well as the manipulator arm itself. So when the cellular morphology was born, that was one of the key technical attributes inside the Phoenix program. But the other attribute of the Phoenix program was, in essence, to demonstrate the system capability to reconfigure a satellite on orbit. And it utilized the cellular morphology and the manipulation technology. But that means you have to send both of those things up, and you have to have a big monolithic spacecraft to hold them all together, and then the robotic arm puts them together and then lets them go, right? What was really, really interesting at the end of that endeavor, sort of the end of my tenure as well, we got to thinking, why do they have to be separate? So this notion that there's a hybrid robotic satellite or cellular architecture eventually translated itself to, well, why couldn't the satellite, if you configured it correctly, also be a manipulator? And why couldn't it reconfigure itself as opposed to having a big monolithic thing that comes up? Right? So that was sort of from the genesis all the way to sort of at the end, what we were thinking. And so to me, the fascinating thing is for us to build anything on orbit, given that mass itself is so critical and so expensive, that you should really find a way to reuse that mass in different fashions. And so that became the construct behind what the Phoenix program was doing. Okay.
That sounds like something that we could talk about for hours.
It is. It's I'm very passionate about it because I think it may not be the end all be all. I'm not silly enough to believe that, but it really opened up the mind and potentially opened up the emergence of high volume, low cost production of small things, small satellites, to could you do even bigger things on orbit instead of just being stuck with a CubeSat and that's all you could do? What if you could merge a bunch of them together, right? So that really potentially, I mean, it's almost unlimited what you could potentially do.
Right. I love this idea. I got a question for you here. What do you think the most misunderstood idea about DARPA is that people have?
So I think one of them is that every idea, there's two of them. One of them, that DARPA only does crazy ideas that will never see the light of day. That is absolutely not true. And the other one is that everything that goes into DARPA becomes a defensive system that automatically nobody ever sees, and it doesn't translate out into the larger commercial marketplace. What's fascinating is that DARPA looks at an entire range of activities, from fundamental research, and they actually fund overseas companies and universities. I did that myself when I was at DARPA, because you never know where that inspiration or where that really cool innovation is going to come from. To obviously, classified and restricted kinds of things. There's no question about it. That's what DARPA has, the range to do all of it. The other thing that's interesting is that DARPA is working very hard and has worked very hard for many years on the construct of transition. So instead of just, well, we'll seed something and we have a good study and it was very cool, and the idea is really look for how do we then transition that into either an entity that is in the military that can utilize it in some way, or into the commercial marketplace. So that's DARPA's sort of really focused, or opened up and widened their focus about their value proposition relative to ideas that they're generated or come in, and then how they get them out into the general public or into the utilization for the U.S. support specifically.
Okay. So not just a creator of weird things that get put into a closet after
exactly
they're bringing them out. All right. You have you co-founded, you're the CEO of this company called Arkisys. It's been around for about 5 years, and I'm curious what the business focus of it is and what you've learned as the CEO of it.
Yeah, no, thanks very much. So, any good professor always has a side company, so that's sort of like a prerequisite, right? But the thing to me that was interesting is after I left DARPA is that I really wanted to try to enable the commercialization of this construct of cellular morphology. The challenge has been, in all honesty, is finding that key revenue sweet spot that it enables, that currently isn't enabled either by constellations of satellites or just one-off satellites that go up and solve a particular problem. So that's honestly, as the CEO of a company, that's one of the biggest challenges. The things I'm told all the time is, Dave, you got great technical ideas, but you got to, the business world doesn't care about technical ideas. They care about making money. So you have to try to translate that into it. There's also a sort of a firm belief that the commercial sector is really the sector that is going to take us into the second generation of space, as opposed to the traditional, the NASA models, or even the DARPAs or other ones, right? Because there's such an explosion in commercial activities in space over the last 5 to 10 years at this point. It's finally, the people are sort of thinking out of the box related to what they can do from a commercial standpoint. So that's what Arkisys focuses, not on research, not on technology. It is trying to take the transition of the cool technologies we had and put them into a market revenue generating construct.
Okay. You have produced over 30 publications. You referred to a couple of them earlier. What has been the impact of being able to get that much a number of publications out there?
Yeah, so it's actually up to I think it's 48. I'm closing on 50. But believe it or not, for an industry person, that's probably a lot. For a professor, it's 1/3 of what theoretically I should have at this time in my career. But that's all right. Honestly, the ones that I'm the most proud of as an impact are the ones that we most recently did with a PhD student of mine and myself, related to an entity that was actually DARPA seeded, but now is a nonprofit entity that's supporting the commercial space servicing industry. It's called CONFERS. And our job was to sort of survey what's been done in particular technical processes that are referred to as rendezvous and proximity operations, because it's traditionally been the construct of nation states, the U.S., Russia, Europe, are the ones that send up spacecraft, and then they actually get together close, and then they merge and do something, right? If we really want to explode this industry of servicing and building and assembling and refueling all that stuff, then there's got to be a very large plethora of commercial companies that are into it as well. So our job was to do a survey of what's been done in the open, and then potentially come up with ideas for metrics that anybody could use to make it safe and as ubiquitous as possible to go up and connect, right? There is no question that space debris is an issue, and the servicing this new market segment relies upon the ability to go up and touch other entities. So the last thing we want to do is to, make more debris, right? It would kill the business proposition as well as the companies themselves. So we put out several papers on that. They were presented at an International Astronautical Congress. So I think, honestly, over the last couple of years, that's the one that I feel really positive about, sharing at least the thoughts behind it and then coming up with potential metrics. We didn't indicate that we had to get it out into the industry, and in particular to get it out to the world, because the idea of servicing being the domain of just a single country is silly. It's not going to happen. It's going to be the domain of all. So therefore, all will share. They call it the tragedy of the commons in space. Everybody wants to use it, but nobody wants to be in charge, right? So, so our idea was to try to make it as open and ubiquitous as possible to actually make connections between entities on orbit so that you can go build and refuel and have these wonderful new markets.
Okay. Let me ask you this as our final question. Is there a frustration or something, one thing about space the way it is right now, this industry, that if you could just wave a magic wand and change it, what would that be?
Yeah, it's a good question. I have mixed feelings about this. The countries must protect their assets and their interests. There's no question about it. So the rubric or the term of national security space is important and it's needed. But what's fascinating is that I'm uncertain if we could make much faster advances in space if there wasn't so much that was restricted by, and it's not just the United States, it's all countries. Sea space is incredibly important, and there's no question about it. But I just sort of wonder, when I take a big step back and you look at the globe, how much more could we be doing, sort of as a society or civilization or humankind, whatever, if we were able to share much more or apply things that countries might say, oh no, we don't want to share that because we think that's important, to general mankind. So it's not so much a frustration, if you will. It's just it's an observation, really. Right. And again, I completely understand that there has to be restrictions. Unfortunately, we live in a world, a place where some people like to take advantage of other people. So therefore, you have to safeguard that. But in general, I'm sort of thinking that, and that's part of the reason that I believe that the next generation and the real explosion in space is going to come from the commercial sector, because their motivation is not to protect, but to make money. And it's an interesting, it's an interesting difference in incentivization. So the hope is that that'll open things up.
Right. Well, thank you for an insightful look there. Dave, if somebody is listening and they're like, hey, I really like what I'm hearing and they want to get in touch with you, what's the best way for them to go about doing that? Yeah,
the best way would be an email here at the Space Engineering Research Center. It's barnhart@isi.edu. That'd be the best way to get a hold of me.
Okay, great. Professor David Barnhart, the director of the University of Southern California's Space Engineering Research Center, CEO and co-founder of Arkisys, former program manager at DARPA. Thanks for being here today.
I really appreciate it. Thanks for the opportunity.
More engineers are not going to solve your problem. It's not a technical problem in that sense. It's a process problem. And the time to fix your processes was 20 months ago, and the second best time is today. This is Jason Kanigan, the president of Cold Star Technologies and the host of this podcast, the Cold Star Project, which is all about identifying and solving process problems for space companies, because that's what we do. And you can hear the entirety of this episode by following the link in the comment below.